So I'm going to talk about my research on wireless artificial intelligence, and so a little bit of introduction. My name is Keivan Navaie. I'm with the School of Computing and Communication and lead the communication group. You know, the formality of the names here are my PhD students, for which I'm going to talk about the results of their work. Um so, as I mentioned, wireless AI is a relatively new notion. The first thing first is to talk about this notion, and then I will talk about the idea of wireless intelligence and talk about some example works on this area. So yeah, wireless realm. I wanted to show you this uh, familiar Etsy illustration of the wireless communication systems, in which you can see, many applications, many vertical industries, and it's basically hard to imagine working without them. Uh, what is important is that basically uh, the radio signals are available everywhere, right? If you go to your, for example, smartphone, look at the setting and wireless communications, you can see a lot of signals from different Wi-Fi access points and also from different operators, right? So also billions of users and also objects are connected to the internet through wireless communication. And during the last couple of decades, basically advances in communication technology, electronics, and antenna design enabled the use of new parts of radio spectrum, which were not available before for communication, like terahertz communication or what is called a millimeter wave communication. And basically, the push from the industry also convinced the regulatory organizations such as Ofcom in the UK and FCC in the United States to take big steps, releasing these new frequency bands for wireless communications. So let's declutter this rather messy network and see what's going on beneath that. So if you look at what's going on in that complicated wireless communication network, what you can see is basically users are connected to the network or the internet through an edge server or access point or base station, a network of base stations and edge access points. In this architecture, if you look at this architecture, you can see that the mobile edge computing plays a central role, right? So we have servers which can do computation, complex computational operations, and they have a large amount of memory, so storage, right? The good thing about this edge computing and moving toward this kind of architecture is being able to have something like near real-time communications, right? And by real-time, near real-time communication, I'm talking about latencies in order of 20 to 30 milliseconds, right? In 5G, and the one step farther in the next generation, people talking about 1 millisecond of latency. And by latency, I mean sending and receiving data, and within that period there is a processing in between. So you send something, you ask for something, the processing happens in the network, and then the result comes to you. So the whole back-to-back transmission is called latency, and 1 millisecond is only available if you have the whole data and the processing very close to the user. So this edge architecture basically enables further integration of computation and communication. So this is basically happening. We have computation and communication meshed together, and we have a lot of data at the same time. And these data, as you could see in the previous presentations, they are called big data because the amount of that data, the volume of that data is very large. They are in different time scales. There are, in many cases, multidimensional data, and they are hard to process. But the good thing is that having this kind of data and communication is basically, we have data, we have computing, we have communication. And if you look at it, these are the ingredients for AI, right? So we have a very big machine of connected objects. They are connected to each other. They have access to computational and also storage capabilities on the edge servers, and then what happens, what remains to be done is to process that data and extract knowledge and vision out of it. So the ingredients basically are there. So if you look at the mobile edge computing, we have the opportunity to basically use AI or any manifestations of AI like machine learning or deep learning, and use that for making the whole process a little bit more efficient. So this is the first thing comes to the picture. So using or commoditizing physical and signal processing design to overcome the complications we always have with wireless communication, because the wireless channel is varying over time. It is a function of time, space, and also a function of other people's activity in the vicinity. So it's a very complex system. But on top of that, so that was the trivial use of AI, and it has been considered as part of 5G. ITU and other standard organizations are working on the framework for standardization of using AI in the communication systems and making them more efficient anyway. But there is another dimension to that. New frequencies which were not available before for communication, they can be used for sensing as well. Like the one in terahertz communication, they haven't been available for wireless communication before because of the loss in wireless communication, because of the technology. Yeah, right. So we couldn't use them because the technology was not there. But the technology is there now, and we can use that part of the frequency for sensing and communication in a simultaneous way. So joint wireless communication and sensing. So what happens is that we have deep learning, we have sensing, and we have active radio waveform. And if we put them together, it is like we have a vast ecosystem of connected devices. And these devices many of them are smart devices. So it's like the brain. So we have a lot of basically neurons. They are connected to each other, and they can process data. And on top of that, we have good progress in deep learning. These days you don't need to be worried about security issues when you do model training. You can do it in like federated learning style. You can also go for unsupervised learning techniques, so you don't need a lot of annotated data, and the sensing can be something which is commoditized by the AI and used in favor of the whole process. So if we want to provide a definition for wireless AI, is a combination of deep learning and sensing and active radio waveform, which creates a new class of use cases that can intelligently add value in a variety of applications and services. In other words, basically, wireless AI uses this vast wireless interconnected system of objects as an adaptive sensing machine to feed the AI. So we have an adaptive sensing machine, adaptive data collecting machine to feed the AI. Let's have a closer look and see what is the AI, what AI can do for us. So if we look at the data life cycle in a wireless communication network, so we have entities who are receiving data. We have entities which are custodians of data, like the cloud service providers, edge providers. We have data consumers, like the individuals, the governments, industry, etc., etc. And we also have data generators, right? And given the fact that we have smart objects connected to the internet, they are everywhere. And they collect data in different time scales. Some of them, they generate data every 1 millisecond. One of them generate data every day, so in different time scales with different kind of meaning and implications. So AI can enhance and change almost every step in this process, right? So for example, predicting the trend in different time scales enable proactive control, right? So if you can predict what is happening in the future, you can proactively control and basically allocate resources to ensure a consistent quality of experience provisioning to the user. AI principle can be also applied in multiple time scales on different aspects of the application, and basically cover the whole life cycle. So as you can see AI when we sense data. You can see AI when you do the network device control, when you have access, when you generate data, when you basically predict the situation of the system, in deployment, in design of the network. So as you can see, in different time scales and different dimensions of the network. For example, using AI, you can have autonomous network in which you don't need to calibrate and configure every single network entity, and it basically provides you a lot of gain on the overhead. My research in particular is focused on what is shown here as data custodians and data generators. So the part of the research I'm going to talk about and show you some simple examples are basically in these two parts of the whole data life cycle. And I show you some use cases and ways of working with the data and this huge machine of data generation. So the first example I'm going to show you is wireless AI application in surveillance and crowd management. So as I told you, we have a lot of tools in our toolbox. So the wireless communication technology has been progressed during the last two, 3 decades, and basically we can do whatever we want with the electromagnetic waves, and we are getting very good in processing signal. We can do it efficiently. We can change the setting of the transmitters and receivers very quickly, and we can do active and passive sensing. What I'm going to talk about in this particular use case is something which is called passive sensing. So the idea is the following. We have radio signal. We use them for communication. We transmit them like everywhere. So we have an antenna. We transmit the data. Everybody receives in the area receives the electromagnetic wave generated by the antenna, transmitted by the antenna, and some of these electromagnetic energy and electromagnetic waves, they are reflected back to the transmitter, right? So you receive some signal that you already transmit, and this reflected signal has features of the objects and the environment in them. So this is the main principle, which is also used in radar systems. So you transmit something, you get reflection back from the object, and then you can see, for example, a jet is basically moving toward you, or basically moving away from you. So the same principle is used here. So you have receiver which receives the information you already generated, and the waves you already generated to transmit data, not necessarily to send something. You already transmit that information to transmit data. So nothing has been changed in the communication system. AI that sits on top of that, look at the received signal, and we can do many things with that. Of course, it's not an easy task. There are features. We need to look at the features. We need to find that features, and we can do many things. For example, you can see number of peoples. You can even predict whether one of those people in the area, they fell, right? One of them is armed. The other one has some kind of fever, or even their moves, right? And all of that is done without intervention of camera, and it's not detectable, right? So basically, combination of sensing in various bands, we can do this in a very more complex way. For example, you can do a health check in a shopping mall, or you can do any kind of crowd management. If you are looking for doing surveillance in a very crowded area, you can do that, and this is undetectable, and the security and the privacy concerns are not as serious as what they are in camera intervention. And in many cases, for example, if you look at guns and things like that, and weapons, having wireless communication system is much better than having X-ray detection in terms of exposing the subjects to a deadly radiation. So you don't have that here, but you can do it very easily and in a safe way. The other application of wireless AI, in which and for the previous one, you can there are some references I show you at the end, and you can always go to my webpage on the university website and get the references there. So another application of wireless AI is dependable connectivity. And dependable connectivity means that we have always access to reliable, secure, and timely communication. So, and if you don't have that, it means that you can't basically depend on the communication framework. I mean, for example, if you imagine an autonomous car operating in a crowded road and all of a sudden its connection with the edge or cloud is lost. So you can't depend on that. Of course, dependability is a cross-system kind of concept, but you can focus on connectivity as well. So in many applications, you might need to depend on the connectivity, and if you lose the connectivity along the way, there might be major risks. So AI can help in this kind of application. AI again can commoditize various components of the system and transform and generate basically data into actions which provide basically some kind of dependable connectivity. As you can see, for example, you have models of the objects moving around. You have models of the network and edge servers. So you can proactively plan for whatever eventuality which is going to happen in the future. And by planning ahead, you might significantly reduce the probability of basically getting disconnected from the network and not receiving the data. And of course, on top of that, in a local onboard system, you can set another process which acts as a standby with a degraded kind of quality of operation. The other and okay, you can see my or previous recent work on dependent information exchange if you're interested on the topic. The other one is indoor positioning and navigation, and this is very interesting to know that even though wireless communication has been changed and progressed during last years, indoor positioning is still an open issue, right? So you don't usually have accurate indoor positioning system. Basically, unlike outdoor communication, in which you use satellite signals for references and beaconing and finding the solution, it's very hard to receive those kind of signals indoor because of the loss in the transmission, and it's really hard to do accurate and interoperable kind of indoor positioning by using the conventional systems. What we usually do is something like with fingerprinting. So it's a very primitive kind of approach. So we have a mesh, and in each node, basically we look at the received signal, we measure the amplitude of the signal, and then when you have an object which is located in between, we compare and find the best and most suitable location adjacent to that and make a kind of estimation of the location. So as you can see, it's a very kind of dodgy way of doing that because, of course, the signal amplitude is affected by many things. And even if somebody walks around, a given point, then the amplitude of signal might be affected, or even the furniture setting in the room might change the pattern of the signal received. So there are ways to doing that. For example, looking at the Wi-Fi signals and fingerprinting, but you cannot expect to have a good accuracy. So 2 to 5 meter accuracy is what you can get out of just pure Wi-Fi and signal measurements. If you put AI on the edge, however, and combine different kind of information together. For example, you have some kind of side information about the map of the area, about the setting of the area, about multiple kind of sensors in the area, even the camera in your phone, then you might be able to put them together and find a better estimate for your basically location. In one of our recent works, we managed to do that using AI, a very simple setting, an unsupervised learning setting, and we could get a very good accuracy, sub-meter accuracy with the same setting without adding anything. The only thing we add is some kind of computational complexity, which is already available in the edge of the network, and you can get a very accurate in sub-meter scale accurate positioning in a fraction of millisecond. So it's very quick, and it can be used it can be used in many kind of applications. Another application of AI in wireless communication we are going to talk about, and by the way, these are the works of my PhD students, Emad and Somaya. Another application is basically caching and content placement. Back again to this familiar picture. Okay, there is a communication network. People are connected to the internet through wireless communication, a combination of wireless communication and fixed networks. The fact of the matter is that, about 60% of the downstream traffic in the network, in the internet, is streaming services, right? So streaming services means that you're watching a TV show on the internet, and the content is provided to you through this complex network of objects and smart entities. So streaming is a booming industry, right? And it remains to be a very important part of the communication. Caching is very important for streaming, and by caching I mean you bring the content closer to the user. So instead of, for example, when you look at your favorite, when you are going to watch your favorite show on Netflix, you are not exactly connected to the Netflix in California. You are connected to a hub which has your data in it, and it has been downloaded on that, using different kind of technique or during different time of the day. So the content is strategically placed close to the consumer of that content. Of course, in Netflix and other content providers, they usually use a combination of optimization and machine learning techniques to do that. But this is only about the content. In some cases, you need to have the processes close to the user. For example, if you are doing something in real time, you need to have the process very close to you, so you can do the processing in an edge node, which is very close to you, to reduce the latency, right? So. So AI basically can train different kind of models for the users, for the network, for the taste of the users in watching and accessing content. And it's not just for streaming, it could be for any kind of critical application. And, it reduces the carbon footprint, one of the most important things. When we look at the communication networks and sustainability and their importance in our day-to-day life, we need to look at the negative side of it, which is carbon footprint. And of course, the communication, every single bit you transmit over the internet, it energy, and you need to transmit it in shorter distances to reduce the energy and transmit less of that data to reduce the energy. And of course, there is a trade-off between computation and communication, computing and communication, which needed to be taken care of in the whole process. So some preliminary results on caching and importance of caching and using caching can be found in our recent results available on the internet. So this brings us to the last slide. So if as a summary, if I'm going to give you some takeaways, basically we have a vast connected system of intelligent objects, and we already know that radio signals are available everywhere and form a vast ecosystem of smart objects connected to each other. Edge computing facilitates having capabilities for unlimited computing, virtually unlimited computing power and storage capabilities, and AI provides the way to basically use that capability and process the data. The other thing is that basically AI can use this interconnected system as a tool, as a commodity to send, to feed the data into the models and basically change and manage various resources in the network. And we are lucky that we are in the right time in which the technology is there, and many aspects and entities in the wireless communication system can be easily commoditized by the AI, can be monitored and controlled and configured by AI very efficiently and very quickly. Combining deep learning, sensing, and active radio waveforms, basically it creates a new ecosystem, and you can have new classes of use cases. There are many new services are going to be introduced in the future based on the same concept. So we have data, we have computational capability, we have AI, so we can get different kind of knowledge out of it. I showed you some instances, including crowd management, surveillance, dependable connectivity, indoor positioning, and content placement and caching. You can expect to see many more examples in the future. So it was basically the end of my presentation.